Hello, everyone. Can somebody use the chat to let me know that you guys are hearing me? Okay. So let me yeah, let's go through the deadlines this week. We have two deadlines. One is lab 1, which is on Friday, and the second one is the quiz. The quiz will be released today after the class, somewhere around 2:30. And as I mentioned previously, you will have 4 days to complete the quiz. Anytime you start the quiz, so about 4 days actually, because the deadline is Friday, 11 a.m. So anytime you start the quiz, you will have about 2 hours to finish it. But then you can start your quiz anytime you want from now until Friday. I actually wanted to let me show you one video about the quiz, and then I really found it very interesting. That's why I'm eager to share. For some reason, just bear with me.
There are limits to your working together. There are limits to your work.
Okay, now. Okay, now let's go with it. Hopefully you guys can hear. Now I guess you guys can see at least.
Together. You're going to be hearing this from every single instructor this week, right? You've probably already heard it 6 times. Don't cheat. I think that some of what people tell you about this is nonsense. For example, people will tell you that you're hurting your fellow students by cheating. That would be true if this course were graded on a curve, but it's not. Grading on a curve is evil because it makes you compete with each other instead of cooperating. So you are not hurting anybody else by doing well in the class. Another thing that I've heard people say that isn't true is that you are going to harm the reputation of the University of California if you cheat. Now, come on. Every 3 or 4 years, some football player rapes a townie at a fraternity party. And that's terrible, but the reputation of the University of California is pretty good. So that's not why you shouldn't cheat. Here's why you shouldn't cheat. You guys right now are constructing the person you're going to be for the rest of your life. Human behavior is mostly a matter of habits. People talk as if you make big decisions all the time about what to do, but that's not true. Almost all the time, you just do what you're in the habit of doing. If you get in the habit of cutting corners this early in your career, you know, how are you going to make it through the harder upper division classes? And then, what are you going to do when you actually get a job and the person next to you isn't doing the same thing you're doing? Okay, you're not going to be able to look over somebody's shoulder, but you are going to be able to find ways to cut corners. And I don't want to fly in an airplane that was programmed by somebody who cheated in his class. Okay, so really, and furthermore, what's the best thing that can come out of cheating? You condemn yourself to a life of doing something you don't know how to do and don't like doing. Okay? So don't cheat. If you do, you're really hurting yourself.
Yeah, I really liked the reasoning there, so I decided to share. Okay. Now, okay, I accidentally got out. Do you guys hear me now? Okay, I'm so sorry. So that was a lot of time we spent on this. Okay, let's go ahead with the lecture now. So we were talking about implementing safe mode transfers. We talked about 3 types of mode transfers that could happen: interrupts, system calls, and exceptions, or traps. We're going to talk now about how we can implement them. The goal of implementation is really to make sure that the buggy and malicious users cannot corrupt the operating system or the other program. So that's the goal of this implementation that we're going to talk about. So to do this, we have to carefully implement this mode transfer. So the question that comes up now, when a user program calls a system call, it puts the arguments of that system call on the stack, and then it calls a function, right? For instance, if it wants to open a file, it says this is the address and these are the arguments, how I want to open the file. Now, can the operating system really use the user stack to execute the system call? Again, think about this. Every time we want to basically execute a function or a procedure or a routine, we need a stack. So now the question is, which stack can we use? The stack pointer, when the program calls a system call, is pointing to its own stack. We really cannot use the user's stack, because what if the user stack pointer is not valid? What if it has been used by the programmer, so we don't really know the state of the stack. And then the other reason that we cannot use it, exactly, we cannot trust the. So I got two answers here. Both of them were correct. We cannot trust the user. The other reason about the security here is that you could have multiple threads, right? So even if the stack, even if it is correct at the time of the calling, the other threads could still have access to that stack. And the other threads from the same process can corrupt that stack. So as a result, we really cannot trust and use that same stack. The solution is basically to use another stack inside kernel memory. So this is a pattern that has been adapted in kernels. We have two stacks for each thread. One is the user mode stack that we talked about. This is the stack that thread uses as it executes. And then we also have another stack inside the kernel for this particular thread that will be used by the kernel whenever kernel wants to do stuff about this thread. So there are two separate threads two separate stacks for each thread. Now let's look at it. So assume that whenever you have a user thread, kernel, before launching that thread, creates a space for a stack for that particular user thread inside its stack, inside its memory. Now that stack is empty initially, right? User starts running. Let's say it starts running its main. It pushes stuff on the stack. It calls procedure 1. It calls procedure 2. So the stack inside users space is basically growing. At some point, let's say user calls the system call. So it pushes everything on the stack. Now the stack pointer is all the way there, as you can see. Now we're going to do a mode switch at this point because we're going to go to the kernel. The way it's gonna happen here now is that we're going to push on the stack for this thread the CPU state of this thread. So whatever registers that we have, we need to save them. So we're going to use our stack inside the kernel for this purpose. So we push everything there. Then we use this stack to handle the system call. So whatever arguments we need to push on this stack, whatever function we need to call, it's going to happen using this second kernel stack. And let's say at some point we need to go and talk to the disk, bring the file. So we need a stack for the driver. We again use this as stack. Suppose that, okay, the driver is done. We pop up the frame associated to the driver. The handler is also done. We pop up the frame. Now it's the time for us to switch back to the user program. We have the user's state right before we do the mode transfer on top of the kernel stack. All we need to do is to basically resume from there, right? So this is how it would look right before we go back to executing our user space thread. So we have the state stored on top of the kernel stack, and the state or the stack of the user looks like that. So now that we are done with the system call, we can pop up the system calls frame from the user stack as well. And now we're ready. So this next time that the user gets to execute, we're going to just pop up everything from the kernel stack to resume the thread. I got a question. Does the kernel only get one thread, or can it have more? It can. It can have multiple threads. So please distinguish between these two. So we're talking about user threads and kernel threads. You could have a multi-threaded kernel. So inside the kernel, you have multiple threads running. And let me publish this. And you could also have processes, each one of them multi-threaded. So yes, the answer to that question is yes. Okay, now let's go a little bit deeper. That was the big picture. A little bit deeper to what really happens. We need to automatically, in a transparent way, transfer the state of the thread that was running to the stack. We need to take a snapshot of the processor registers, right? Now, let's say that the processor was running this thread. So this is a user level thread. We're in a function foo inside the while, and we're doing stuff. So this is how user stack looks like. The foo is on top because we're basically there. So the PC program counter is pointing somewhere here that we're executing. The stack pointer is pointing to the top of the user stack. We have a bunch of flags. These are important flags related to the computation over there. And then we have all the other general purpose registers in the processor. Now, let's say interrupt happens, or a system, because I don't have a system call in this user code. Let's say an interrupt happens. What can happen? What should happen at this point? We need to take a snapshot of all these things, right? The first thing that happens is that the moment interrupt happens, hardware, please make sure that you focus on this, what I'm saying, hardware pushes a bunch of stuff on the stack. So this is done by the hardware. We're not talking about the kernel. In a moment, I say why hardware has to do this. But then what hardware does is hardware pushes SP, stack pointer, pushes the flags, and pushes the PC to the kernel stack. And then some space here for errors that could happen after you call the handler. Now, let's pause here. There are two things here important. First of all, hardware should know where the kernel stack is. It has to have, other than this SP, this is stack pointer, right? Has to be pointing to the stack pointer of the running program. So we should have another register that will be set by OS to point to the kernel stack. So every time kernel schedules a thread, it also sets that register to point to the kernel stack, right? So that's first one. So hardware has to have a pointer to kernel stack because hardware is pushing stuff on it. Now the question is, why should hardware do this? Why can't kernel push these registers to its own stack? I would usually pause here, but since I don't have a physical live audience in front of me, I'm going to answer that question. So the reason that we cannot do this in the kernel is because the moment we start running kernel code, PC already has to point to the kernel code. So PC has already changed. Program counter is now pointing to kernel code. So what was it before? What was it when it was executing the user code? We don't know. So PC has changed. So there is no way for the kernel to push PC now to the kernel because it has actually changed. The same with the stack. So the moment we're running this kernel code, the stack pointer should point to the kernel stack. So if we want to make a copy of it, it would be a wrong copy. That's why we have to trust the hardware to do this for us. So that's let's put that aside. Now after that, what does operating system do? The first thing the kernel interrupt handler does is it executes this push AD instruction or its equivalents in other architecture. And what that does, it basically pushes all the important registers to the stack. So now the stack pointer is like previously a stack pointer was pointing to the kernel stack, so it's pointing to the right thing. Now we execute push AD and we push all the other registers because these ones are safe. We haven't changed them. So the other general purpose registers are safe. We can definitely push them, and whatever they have is whatever they had when we were running the user code. So they're safe, we push them here. And then, so that's basically the two important steps right after we switch. One thing that I usually ask students to think about is that if you look at this, you see two SPs, one SP here and one SP here. So you might ask, why are there two SPs? What was the point? The answer to that is a question. So are they the same really? Are they pointing to the same things? This one, the first one you can see, is pointing to the stack of the user stack. What about this one, this SP? Where does this one point to? So this one was pushed on the stack after we executed push AD. So this one actually points to the kernel stack. So each one of these SPs are pointing to a different stack. Now, you might ask, why do we need this one? We actually don't need it. So it's being pushed here because of this instruction. So this instruction push AD pushes everything. So it pushes things that we actually don't need. And then when you execute pop AD, which is which is to basically pop everything now, it actually disregards SP. I got a question. Did you say the kernel allocates a separate kernel space stack for each user thread, or does it share one between them? Okay, so this is a good question. So kernel, it's basically architecture. It depends on kernel. So kernel could potentially have one stack and use it for every thread, but that sounds very inefficient. So in usual cases, the mainstream kernels, you have one separate thread, one separate kernel space stack per user thread. So kernel allocates separate stacks for each thread. Now I got another question. So just to clarify, the OS saves user state to the kernel stack. Yes. So by executing, let me publish this one. By executing this, I guess I published the wrong one. So by executing push AD, you are taking a snapshot of your user state. This is not complete, as I mentioned, because the PC and SP have changed. So we trust the hardware to make a copy of those two, and also E flags. Those also could have changed. So we trust the hardware to make a copy of SP, E flags, and PC. Okay. Now that we talked about user to kernel mode transfer, let's talk about kernel to user mode transfer or mode switch. This could happen when you create a new process, for instance. So you create a new process, you create a new thread, you prepare for that inside kernel space, and then you move to user space. So that's a mode transfer from kernel to user. The other one is when you return from interrupts. So you have been, handling the interrupts. Now you come back to the user. The other one is when you want to context switch between processes or threads. You have to come to the OS, to the kernel mode. Kernel decides which thread to run, and then it transfers again the mode back to the user. And the last one is user level up calls or signals that you hopefully remember from ECE 252. So this is another one. So when a message or a signal comes to a thread, we're really getting the message maybe from another process. We come to the kernel, we process that signal, what has to happen with that, and then we transfer mode to the user when we deliver that signal. I got another question. It says push AD will push incorrect. Will push incorrect SP and PC, right? So it actually doesn't push PC. It only pushes SP, and it is incorrect in a sense. So the SP that is pushed is the SP that you have at that point, which points to the kernel stack, and you don't really need it. So that's why when you pop AD, you disregard SP. Okay. So here is an example. So let's say we start executing a user thread. That's when we have a mode switch from kernel to user. Then at some point we exit. That's again a mode switch from user to kernel. During the execution time, we could call system calls. We can return from them. An interrupt could happen. And then let's say, for instance, in that case, the kernel has to go and see what has happened inside the hardware. Let's say that was an interrupt for I/O. We get that, and then we may go back and forth. Eventually, we return from interrupt. So that's RTI. We return from interrupt. Exceptions could happen. Let's say the user code divides by 0. In that case, again, exception happens, mode switch happens. And that's pretty much it. So I got another question. Why does the handler even have the call push to begin with then? Okay, so as you should remember, the purpose of doing this diligently is to make it transparent to the user code. So we don't want user code to even notice this, right? So we have to take a snapshot of the user state, because when we're done with interrupt handler, we want to resume that thread. That's why we have to take a snapshot. And the way we take a snapshot is by saving the registers of the processor. So that's the state of that process, that thread, that we have to take a snapshot of. That's why we push them on the stack. Okay, so we're done with that one. Now, let's talk a little bit about the system called interface, which is an important interface. We'll deal with it during this this course. I got another question. What interrupt hardware access does user mode have? Oh, what limited hardware access does user mode have? Isn't all hardware access done in kernel mode? Yes. So basically, hardware doesn't have the user program doesn't access hardware. I don't know where you got that idea. So in this picture, you don't see anywhere that user is. Oh, you're talking about this one. So this limited hardware access is basically the fact that your code is running on the processor, or your data is using the memory. So these are the limited accesses that you have. If you remember about that picture we had in the introduction, the protection line basically hides all the other devices, but then we somehow need to provide the registers that your processor has, right? So when you're running a code, you're basically using those registers. So that's an access that you have to the hardware. Can you explain what exec, return, and RFI are? Yes. So exec, hopefully you know. So this is fork and exec. So you start executing a program. What was return is basically when you return from a function. So it's like system call, you return from it. And then RFI, it's a special kind of return that you return from interrupt. There are subtleties in how RFI works that is different from return and normal return. So I don't want to go deep into this, but you can definitely search. So there are very subtle points. It actually in your book, in one of those advanced boxes, it talks about what are the subtle differences between RFI and return. You have to check to see if what you have on the stack is of user type or if it is kernel type, because when you're doing, interrupt handler, you could also push other stuff on the stack. You could call other functions, and RFI checks if it has to pop up a frame that belongs to kernel. It does act like a normal return, but if the frame on top of the stack is a user frame, then it also changes the mode. So it goes from kernel mode to user mode. So it also does that for us. Okay, so here you see the system call interface on top. This is the interface that programmers and programs see, and underneath you have all the devices being accessed by the kernel through subsystems. So if you have your processor, the way kernel manages it through system calls is by process management. Your memory is done by memory management. All the disks are being, offered by file system, and so on and so forth. Now, one piece here that interacts with the system calls is the device driver. So the device driver is actually a code that runs in kernel mode and knows the language of the device. It's usually written by third parties, those who created that device. They also write a program that can talk to that device. But then they have to follow an interface. We don't want, we want a unified interface. So you usually have a specific interface that all device drivers stick to, and that's pretty much basically treating them all like files, which you pretty much know from ECE 252. Now, going deep to the architecture of device drivers, usually what happens is that you have two halves for each device driver. You have the top half and you have the bottom half. So the top half is accessed in call path from the system calls. So when you call the system call, this is the half that is called by the operating system. It sets up stuff. It starts talking to the device, but then it has to be very short. It just does a little bit of things and then disappears or finishes. It's very fast, and then it usually what it does is it will start the I/O, or it starts talking to the device. It could wake up a thread, or put that thread to sleep and finish. Now the bottom half is the half that would be called upon when the I/O is done. So when the hardware is done doing what it was told to do, it raises an interrupt, and that's when we start executing the bottom half. So let's look at it in a picture. This should make it more clear. So let's say the user program requests I/O through a system call. So through a system call, we come to the kernel. Now kernel looks at the data it has. Maybe this is a file that has already been brought up to the memory, so we don't really need to go back to the device. If we have the file, then we just go back and answer. So if we have it, then there is not much else to do. We just transfer data to the process and return. Done. But if not, then we're going to talk to the device driver. This is where we talk to the top half. So from the path of system call, we're going to talk to the top half. So we say, OK, we need this file. Now the driver, the top half, wakes up, sets up stuff with the device. So it sets a bunch of bits here and there. It starts the communication with the device, and it finishes. Now at this point, the device has the commands, so it starts running and executing the request. And then time passes. At some point, it's done. It raises an interrupt, right? So once it's done, it raises an interrupt. So this is when we are going to talk to the bottom half. So once the interrupt is raised, the bottom half is going to wake up, receive the data, maybe copy that data from the device driver's buffer to so it's going to store the data in device driver buffer. So we're still inside the device driver. We might get the data from the device, put it in our buffers, and next we call the top half. Now the top half determines which I/O request it was. It makes all the changes it has to make, and then it calls back to the kernel. It says, OK, here is the data. Now the kernel copies the data from the device driver's memory to the user's memory, and at this point you can just transfer back to the user program. OK, so there are two ways to transfer data from the user program or kernel program and the devices and I/O devices. So one common way is programmed I/O. Basically, to do this, the processor executes a command for each byte of data that has to be transferred between the program that is running and the I/O device. So for each byte of data that is being transferred back and forth between the device and the program, the CPU has to execute a command, like a put or get, to transfer 1 byte. So this is sort of like simple because it's like you're executing one instruction and you're transferring data. But the downside of this is that it basically consumes a lot of processors cycles. So if you're transferring, let's say, a gigabyte of file, then the CPU has to be all the time active for each byte of the data that is being transferred between the device and the program. So to make things faster, the technology that is being used very commonly these days is called direct memory access. So this one, basically the processor sets all the required attributes. It says, okay, I want, 1 gigabyte of file to be 1 gigabyte of data to be transferred from this address in the memory to the device. And then it just commands a controller, a DMA controller, and then gives access to that DMA controller to that region of memory. And then CPU goes and does its own business. And then the DMA controller starts transferring the data from the memory to the device, I/O. So here, CPU just does some preparation at the beginning, and then the rest of the transfer is happening by the DMA controller. I got a question. Is device driver code threads always loaded into the RAM, or is it loaded based on the kernel I/O subsystem specific needs at a particular time? Yeah, so if I were to guess, it would be the second one. So whenever you want to use the device, you could load its code. That's pretty much what I'm thinking. There are certain devices that you always want to have their code, like let's say your network, your other devices that you constantly use. So you might actually keep the code in memory. Okay, so DMA can only occur from the kernel system side, right? So let's look at the DMA in more details. If I don't answer your question, you can ask it again. So let's look at the DMA, how it works. So in this figure, you have your CPU. Yeah, so you have your CPU. It has its cache, and then there's a bus between the DMA controller and the memory. And then you have your PCIe or PCI bus, and then your device here. Now, let's see what happens. So the first thing that happens is that the device driver, let's say it was a system call, so we're running a code in CPU. We call on the device driver to transfer data from the disk to a buffer. Let's say this buffer inside memory. We say, okay, give me data and put it in this buffer. So that's the first thing. Then we start running the device driver. What the device driver does, it sets some bits and controller flags, whatever, inside the disk controller and says, okay, I need you to transfer C bytes from your storage to this buffer. The third thing that happens is that the disk controller initiates this DMA transfers now. So what happens is that this DMA controller now gets the data from the disk and puts it in the buffer. As you can see, after 2 here, we're done. We're not doing anything with the CPU. So CPU is now running other stuff. And in the background, the DMA controller and the disk controller are talking and transferring data for us. And once everything is done, the data is done, the DMA controller raises an exception and tells the CPU, okay, the data that you wanted is done. You can go and find it in the buffer. So this is one example, for instance, how it works with the network stack in Linux kernel. So this is before 2.6. Things have changed a little bit. Let's say, so this is from the other side when the packets are arriving. So when a packet arrives on the physical link, it basically DMAs that data. So the data goes to the buffers of your network card. So this is the buffer for dedicated to that network card. Then you do DMA, and and transfer the data to the memory. Again, if you can see here, there is no involvement from CPU. So once the data is done, once everything has been copied, now your network card is gonna raise an interrupt saying that, okay, I got a packet and it's stored in here. Now we go to the kernel here. Kernel starts copying the file into its own buffers. And at some point when user says, give me the data, we're going to go back to the kernel, read that data, and copy it back to the user. So you might ask, okay, wait, I have written a lot of code. I don't remember calling system calls. I have been, using files and networks and I/O, and I never called a system call. I never saw a system call. And you're actually right. You probably haven't seen any when you were coding. And the reason for that is that it's usually wrapped by your language runtime library. So this is basically the beauty of layering. You call a function, and then inside your in the library that you're using, like libc, is where you actually call that system call. So this is a figure I want you to remember. We come back to it all the time. So if you remember, this middle is where the operating system sits, and it provides the system call interface that we talked about today. And on top of that is basically the portable OS library. And on the bottom is basically where we talk to the devices, where the device drivers are. And if you look deep into your process in how they run, they usually have these OS libraries. This is where the glue part of the operating system comes into picture. Okay, let's just put everything that we saw together with this example. Let's say that the client, the user is sending requests to a web server for files to download. Let's say we're just sending requests for, pictures or whatever. And then the server gets those and replies with the file that was requested. Let's focus on this web server side. In this picture, I have 3 layers: the web server, the kernel that the web server is running on, and the hardware. And in this example, because we're receiving requests from network, we're concerned with the network interface, and because we're dealing with download files, like download requests, we're also probably getting files from the disk. Let's see how it works. So when the server starts running, it has to register itself. That's when it opens a socket and starts reading from that socket, right? So this is the first system call when you want to read from the socket. So you call that system call, you come into the kernel, you wait basically here. And what happens here is that you're gonna be, put to sleep because there's nothing yet. So you're gonna be waiting, hopefully not busy waiting, but just, being put to sleep, waiting for an interrupt to happen. Now, let's say a request comes. What happens? We saw DMA copies the data from the device to kernel buffer. So let's say now the data is here in the kernel. Now an interrupt happens. So you get the data, you put it back to the server's, the web server's memory. You say, here is your data. Now, your web server is going to parse this request, see what is being requested. Let's say it pinpoints it to a particular file. Now it runs, it basically again calls a system call to read the file. So this would initiate a disk request that potentially is processed by another DMA. So the data is now back to that buffer. And then you come back to your web server. And now at the end, you have the data. You're going to just use another system call to write your data back to this buffer to then send it to the destination. So here you can see 3 system calls. This one also has to have a system call, but it is. So basically, this is one system call to read from the socket. This is one system call to read from disk. And then this is a third system call to write to the socket. So the RTU is basically returning. That's what I mean, return from kernel to the user. Somebody asked what it means. It doesn't really mean a particular instruction. It means returning from kernel to the server. Okay. So, and then this is the summary of what we talked about. Really, in essence, we talked about threads, talked about address spaces, talked about process. So the process, if you remember, is basically the combo of an address space and one or more threads. And then we dedicated a good portion of this lecture on dual mode transfer, how we implement it. So I'm going to give you guys 2 minutes to get up, stretch, and then we will continue with lecture 3. So I'm gonna continue in 2 minutes. So 1:56 we'll continue. Okay, we're back. So in this lecture, we're going to talk about how to implement kernel threads. We'll also talk about user level threads and how we can use the kernel threads implementation to implement them, and also talk about alternative ways of implementing user level threads. And at the end, we'll talk about implementation of synchronization objects. We'll talk about how to implement mutex, semaphore, condition variables, and such. Okay, so let's recall the life cycle of a thread. So you have the initial phase. when you call thread create, you put the thread on the ready list of the CPU. And at some point, the scheduler will start executing your thread. At that point, the status of your thread becomes running. The thread might yield its time, which would put it back on the ready queue, or it could join on another thread, which would change the state or status to waiting. Once the thread signals it's back on the ready list. And at some point, you're going to execute exit, and at that point, you're done. So this thread is considered finished. So this is the life cycle. Now, if you look at the architecture of kernel threads, this is an important picture that I want you all to pay attention to each particular piece in this picture. So we're looking at kernel as one big process here. So the entire thing is just one big process. So you have your kernel code, you have global variables, and you have your heap, your kernel heap. Now inside, you have multiple kernel threads that are doing stuff, right? So each one of them has its own TCB, each one of them has its own stack, and they're just running their own code. I mean, they access the kernel code, but each one of them is running, potentially running different instructions. Now, if you're managing threads, user threads, so now let's move to the user space. Let's say now I have two processes, user level processes. Each one of them has two threads. If I want to manage those threads by kernel, then for each one of them, as we talked, the kernel is going to dedicate a separate stack. So for each thread, kernel will allocate a separate stack. Kernel is also keeping the TCB for each one of those. And the process itself has its own PCB. The way that users in this architecture create new threads is that the library, user level library, allocates these stacks because this is in user level mode. So the user level library allocates stack. The heap already is allocated because it's inside a process, right? And at that point, it will call a system call. And that call would go to the kernel to create and set up the TCB and the stack inside kernel. And then after kernel handles everything and sets up that thread, then kernel decides which one to run. And at some point, kernel decides to, let's say, run this thread. Kernel switches back to that thread and executes it. So again, the path to creating a new thread starts from the user level library, allocating a bunch of spaces and setting up code and stuff, and then calling a system call, going inside the kernel and getting everything initiated. Let's look at a simple pseudocode for creating a new thread. Let's just dive into it. So let's see. Let's say we get so this is a function. We're going to get a thread t, a pointer to the thread that we want to create. Now, let's say this is the function. We get a pointer to the code that this thread is going to run. So we're going to call that a function. So this is the function. This is the initial point that this thread is going to start executing. And it has a bunch of arguments. So the first thing that we're going to do is we're going to allocate a TCB and a stack. So let's do that. Let's say we have a struct, the TCB struct. We initiate one. dynamically creating one. And then we make the thread that we got its TCB to point to this TCB. The next thing we need to do is to initiate a stack. This is a kernel stack. So it probably has a size, a predetermined size. So we create that. And okay, let me take a step back. So sorry, I think I messed this part up. Here we're going to talk about creating kernel threads. So I apologize if I misspoke about what this is. So we're going to create, let me go back to the picture, previous slide. We're going to talk about these threads for now, kernel threads. We will later on talk about these. So when we create a stack, we're actually creating these as stacks. We're not creating, I mean, it's really interchangeable, but yeah. So if this is, if this is a kernel thread, this stack is basically the stack for this kernel. If it is a thread for a user space, then this stack is basically the kernel stack associated to that thread. Now, as you know, the thread starts from the top of your memory and goes downwards. So after you allocate, you need to set the pointer to the end of it and start incrementing the stack pointer because it basically grows downwards. The next thing we need to do is to set the PC to that function that needs to be executed. How do we do that? Well, we're not going to point to exactly that function. We're going to call a stub before that. And the job of this stub, we'll see how to implement it, is basically set up other stuff and then jump to that function. So we're doing one level of indirection here. So instead of basically starting from that function, we're going to start from a stub. And we'll see why this is important. Now, so basically now the PC is going to point to this stub, which we'll see the code of. But we're going to push this function an argument on the stack so that when the stub is called, on top of the stack, I have the function an argument so that the stub can easily call the function for us. So we push the arguments to the stack. So this is basically a pointer. We decrement, the stack pointer. So because again, it's growing downwards. Then we push the function and we decrement. Now, at this point, we're going to push a dummy frame. Again, we will see why. Bear with me. So we're going to push a dummy switch frame at this point. I got a question. How do we create a new stack in C where we cannot instantiate using... Okay, so I'm not actually talking about so I got a question. How do we create a new stack in C where we cannot initiate using new? Let me publish this. So I'm not actually giving you a code. This is basically just pseudocode giving you the ideas of how it works. Talking about specific things we can dive into it later, or in the office hours I can answer that question. But at this point, I just want to give you the big picture. Again, this is not a real code, real C code. It's as close as it could get, but it's really just to give you an idea. Okay, so going back to this, we push a frame, and now we change the state of this TCB to ready. So we're ready to execute this. and we put this guy to the ready list. So we have a ready list, we add this TCB, and we're done. So that these are the steps that we have to take. Big picture, right? Now let's look at the stub. So we talked about this one level of indirection. Let's look at it. So it's going to get two arguments, the function that it's going to call and the arguments for that function. Now, what it does some startup housekeeping. Basically, maybe, you know, setting the time when this thread is going to execute, and a bunch of other stuff, disabling interrupts and stuff. Again, let's put all of them under one category, let's say housekeeping. And then it's going to run the function. So it's going to say function arguments, run it. I got another question. How does this protect the stack from growing past the pre-allocated stack size? It's not going to, right? At this point. So we're talking about thread stacks. We talked about how you can potentially prevent overflowing your stack. You can put something under at the bottom of your stack, and always whenever you do a context switch, check that variable, see if it hasn't changed. If it has changed, definitely you have probably you have overflow condition happening. But even if it hasn't changed, that doesn't mean that you haven't overflown. You haven't, you know, exceeded the size. So, okay. Now, let's say at some point this function finishes. We come back to this stub, and we're going to call the thread exit. If the thread really didn't call this, we're going to call it. And if it has called it, so what? We call it again, nothing will really happen. Okay, so let's look at it. So what happens? Let's say this was let's say a user level process called system call to create a thread. So the kernel initiated the stack, pushed the stub, and at some point, this stub is going to switch mode and start running this function inside the thread stack. So to just give you the idea, so this stub is going to stay in the kernel stack, and it's going to just call the thread stack. So I got another question. So when we run the function, it's running on the user thread. Yes. So I mean, depends. Because of the architecture we're talking about, the multi-threaded kernel, we could be running kernel threads, or we could be running user threads. So I think in the slides and the pictures that I have, I'm assuming that you have a user level thread that has called these system calls to run the thread, but it could well be that these are just kernel threads. So everything happens inside the kernel. I got another question. How does the stub access the function and arguments? Well, that's a good question, but so see, the stub has these two arguments, right? The function and the arguments. And we have already pushed these two on the stack before calling a stub. So we pushed them when we were creating this thread. We pushed the pointer to function, we pushed the pointer to argument, and then we called the stub. So when we are inside the stub, when its stub looks at its kernel, its stack, on top of the stack, it actually sees these two. Got another question. So does kernel thread have double stack as well? No. So if you're a kernel if you're a kernel thread, you only have one stack for yourself. Okay. So coming back. So what do we include inside the housekeeping? This could be, again, as I mentioned, recording the start time of the thread, other statistics we want. And then it could be, I mean, it should, if we are switching to a user thread, we have to switch mode from kernel mode to user mode. We'll talk about an invariant that we have to implement throughout our implementations of threads. That invariant could mean that at this point we have to enable interrupts. We'll talk about this in a lot of details. And it has to change the status from ready to running, right? Because now we're running the thread, so the state is now running. And then we have to pay attention now that the kernel thread will grow this way, and then both of the stacks will grow, could grow. The thread stack and the kernel stack could grow. And finally, when we're done with the thread and we come back, we're gonna, if the thread has not already called the exit, we're gonna call it inside the stop. Now let's talk about context switching between threads. How much time I have? So I'm gonna actually go a little bit over time today. So I apologize. So I'm gonna go until 2:25. So I assume that I have 12 minutes left. Now, let's talk about context switching between threads. There are two ways that you can context switch between threads. One is a voluntary context switch. The other one is an involuntary context switch. So the voluntary one is usually when you call thread yield, thread join, or thread exit. All three of them, you voluntarily yield your CPU time. The involuntary way is when you got preempted. Either an interrupt happens, let's say the timer interrupt goes off, or an IO happens, or maybe an exception happens. So you get preempted. You didn't want to to lose your access to the CPU, but you get interrupted, and you lose your CPU time. So what's the difference between these two context switches? Usually the voluntary ones involve the thread library functions. When you basically do thread yield, you usually go to the, if it is a user library, if it is a user level code, you usually go first to your library, your thread library inside user space. And from there you call a system call. So from the thread, you go back to the system library, still inside the user space. And at some point, you're going to call probably the system call. Or maybe in some cases, you don't even do that. We'll talk about alternative ways of implementing user level threads. So it could well be that at none of it, you will call system call to switch. Whereas if it is involuntary, then usually, again, you're going to actually switch back to kernel. So if an interrupt happens, you're going to go to kernel. So there is no transitioning from the user program or user thread to the user library and then to the kernel. So you're going to immediately go to the kernel. Let's look at an example. Let's look at yield. Let's say we're computing pi and we have a while. And each time you compute one next digit and then yield. And then when you get back the control, you compute another digit and then you yield. And again and again and again. So let's focus on this. To see how it works, let's see how threads get switched first. What we want basically is to have a function that as an input gets two TCBs, an old TCB and a new TCB, and then switches from this new TCB to from this old TCB to the new TCB. So basically, we want to implement this function. As an argument, we have two TCBs. We want to switch between them. So the first thing you do you push the registers onto kernel stack for the old TCB, right? So you call push AD. When you do this, you basically take a snapshot of the registers for the old TCB. Then you're going to save the old TCB's stack pointer. So this one, old TCB SP, please remember, so this SP is probably saved by hardware for you, right? So we're not going to talk about the mechanism that you have access to this SP, but at this point, you're going to just save it, assuming that we have access to this SP here, potentially by hardware. Hardware pushed it to the stack, so we have it. Now we just set it. We say, okay, old TCB SP is going to be this stack pointer. Now we're going to switch to the new TCB at this point. So we have taken a snapshot of the old TCB. Now we want to switch to the new one. Well, we're going to change the SP to point to this new TCB SP. So we change the stack pointer. Now the stack pointer is going to point to this new TCB's stack. And we're going to pop the registers from the kernel. So one thing I have to point here when we're talking about the stack pointer, please, I think I'm sort of confusing you, but here we're talking about the kernel stack pointer because now we want to pop, right? So here the stack pointer was pointing to the, because we're actually running this code inside the kernel. So the stack pointer, so I take it back actually. I wish there was a way I could go back in time 2 minutes ago, get whatever I said back. So this SP here is actually the stack pointer right now because it's pointing to the kernel stack pointer. And we save the kernel stack pointer to this old TCB stack pointer. So this, again, I emphasize, is the kernel stack pointer. Now we change that stack pointer at this point. We're going to switch to this new TCB. So we take its stack pointer and set the stack pointer to this TCB. And now we're going to pop. So we pop AD. Hopefully, at this point, I have a snapshot of this new TCB on the kernel stack that I am going to pop. Because this new stack also has to have a snapshot of it stored on the stack. So I pop it, and then I return. That's it. So I got into this function as old TCB, and I got out of this function as the new TCB. I got a question. Question in general. For this week's quiz, what part up to in the lecture would it cover? So to whatever I finished today. So each quiz covers all the way up to the lecture before it. Okay, so here is one question, one tricky question. Where does this return to? So when I return here, where am I returning to? So I got a question. Does pop AD pop what you just pushed from the push AD? Good question. Not really, right? So here, this push AD pushed the registers to old TCB's stack. But then here at this point, I changed the stack pointer. So now a stack pointer is pointing to new TCB's stack. And then when you execute pop AD, you're going to pop everything on that stack. So you're not really popping everything you just pushed. You're popping whatever that was pushed before, some times ago, on this new TCB's stack. And when you return here, yeah, exactly. So I got an answer to that question. You return this return. If you remember that, I think it was last lecture, we talked about how a stack grows. So on top of the stack, we put the return address. Every time we call a function, on top of the stack, we have the return function. So whenever a function returns, to find out where it should go, it looks at the top of the stack. So at this point, when you want to return, when you execute this return, you're going to look at the top of your stack. Which stack? Well, now the stack pointer is looking at this new TCP's stack. So whatever you stored on top of this stack, you're going to return to that one. Why does this get really important? So we're going to return to the address stored on new TCP's stack. So now we can actually look at yielding. So you had the stop on your kernel stack. You called compute pi. And at some point, compute pi called thread yield. This thread yield traps to kernel and calls this system call, kernel yield. And this guy is going to call the run new thread. We're going to pick another thread to run. And let's look at the code for this run new thread. So the first thing it has to do is to prevent interrupts from happening, disabling interrupts, because we talked about this actually. Whenever you're doing interrupt handlers or system call handlers, you don't want to do them inside each other. So you want to get done with one and then go and do the other ones. That's why you disable interrupts here. Sorry, I'm going over time. I have to finish this slide and then I'll finish this this lecture. So you disable interrupts. You choose a new thread. This is where the scheduling happens. So from your ready list, you get a new TCP. You pick that one. You change the state or status of the running TCP to ready, and you put this thread to the ready list. So the running TCP now becomes ready because it called yield. And now we want to switch to this chosen TCP. That's where we actually call the thread switch. So we have the running TCP that we just put it to the ready list, and we have this chosen TCP that we want to switch. Now we call thread switch. As you can see, the run new thread calls thread switch. Okay, now the question is, very important question. What do we push to the stack when we call this thread switch for return address? Again, remember, the stack is used exactly for this purpose. Whenever we call a function, we put at top of the stack the return address. When this function is done, you want to return. So what do we push here before calling this thread switch? Well, we're going to push the address of the next line. So the address of this next line inside this new thread, run new thread function is pushed on top of the stack for this running TCP. And then we switch, and then we start running this thread switch. So let's say after we come back from this thread switch, we're now again running. If you come back from this thread switch, you changed your status as running. Now the question is, when exactly do you execute this code? This is again another important question. And the answer to this is whenever another thread switches back to this thread. So after you run this thread switch function, you're going to start running this chosen TCP. So everything will be paused here. So nothing will go further. You start running this chosen TCB. At some point, this chosen TCB also yields on, or an interrupt happens. And then this chosen TCB also runs thread switch the same way as this one. And maybe, lucky for us, we get to be the chosen one then. And then when we execute the thread switch, then we're going to come back here and start running this. Why? How do we come back here? Because on top of our stack, we push this next line that will be popped when thread switch is called. I'm going to just go back to the previous slide. Here, see, when you call return, you're going to return to wherever address that is stored on your stack, which here we actually store the return address after this thread switch. So a little bit of mind game, I would say, here. So I'm going to end the lecture here. I'm so sorry for going over the time. Yeah, on Friday we'll review this and then we'll continue from here. Thank you and take care. Be safe. Talk to you again on Friday. Bye-bye.